Hello, our lab project is titled Magnetic Flux. So for our lab, we are going to be using magnetic flux to solve for the magnetic fields of a given magnet. Magnetic flux is the magnetic field moving through a given area at a certain time. And using a change in magnetic flux, we can induce a current. And that is demonstrated by Ampere's law, shown here. So how we are going to apply this is we are going to have a magnet and a current carrying ring. And how we're going to have a change in magnetic flux is we are going to move this ring up and down at a given frequency. So this change in flux should create an induced electric current. And we have this ring connected to two wires, and we're going to connect those wires to a voltmeter to measure the voltage drop of the ring. And using that as our electric field, we can then solve for the changing magnetic flux, and using that flux, we can solve for the magnetic field due to the magnet.
I'm Cindy, as you may or may not know, and I will be presenting the apparatus for our physics experiment, magnetic flux. Alright, so this is all the apparatus that we use. So, firstly, you will need a solenoid, right? So this is this little contraption. And then you will need this Pasco tool. It is called the wave driver number 2. And it is what you will be using to create, like the waves and the frequency. And you will also need a magnet of unknown strength, 2 rods to set up your magnets over the solenoid contraption, and a clamp to make sure that everything is steady. And of course, you will need your Pasco interface. This is our universal 850 interface. And you will use it to record the changing frequencies. You will also need a trusty laptop to record, to view the changing frequencies. And finally, you will need a multimeter or a voltmeter, whichever you have on hand, to, record. Yes. Hello again. Before we start talking about procedure, let's maybe look at our setup here. So as you can see, we added another rod in order to stabilize our wavemaker too. And our solenoid is positioned between the magnet, and also the magnet is at about halfway through to the solenoid, so the waves can go through adequately. All right, and our wavemaker is connected to our Pasco interface, and the sides of the solenoid are connected to a multimeter in order to look at voltage change. So now that everything is set up adequately, everything is in the right place, we can use the Pasco interface to change the frequency in order to visualize our values. So let us begin with the frequency of 1, as we must begin really low to watch it change. As you can see here, the solenoid is moving.
After using Pasco to find the EMF due to a change in frequency, we put this in a graph in Excel. As you can see here, on the x-axis we have omega, which we put set equal to 2 pi times the frequency, with the frequency being 1 through 9. And then on the y-axis we have the maximum electromagnetic field that we recorded using Pasco. With this, we expected the maximum to be equal to the absolute value of the minimum. However, we got slightly different numbers for these. So what we did was we graphed the minimum as well as the maximum and the mean of the two. And for these graphs, we got the mean of the two to be the most precise, with an r-squared value closest to 1. And so this is the equation we chose to use for the max EMF in the rest of our calculations.
Again, the equation that I mentioned before, which is that electric field is equal to the negative change in flux. And so for our electric field, we are going to be using this equation. And for our Emax, we have the graph we used in our results. So for this Emax here, we are going to be using the equation from our graph, and that is 0, 0, 1, 2 omega for our Emax. And then of course we have cosine omega t. And omega is going to be 2 pi f, with f being our given frequency. And now, in order to get magnetic flux, which is what we're solving for, we are going to take the integral of each side. And so we're going to take the integral of this electric field equation with respect to time, dt, and that is going to give us 0.0012 sine omega t, and that is going to be equal negative magnetic flux. Now, in order to get the magnetic field from our magnetic flux, we are going to relate them using the equation magnetic flux is equal to the integral of B being our magnetic field, dot dA, with A being the area of the ring, and we get that by measuring the radius and then using pi r squared. Once we get that, we can simplify this because the ring and the magnetic field are perpendicular, and to be B times A, and that is equal to the magnetic field. And if we divide both sides by A, we can get that our magnetic field is equal to magnetic flux, which is 0.0012 sine omega t over the area. And that's how we solve for magnetic field using magnetic flux.
Alright, so this section we will be talking our above and beyond, and we decided to do daily applications of magnetic flux. Our very first application is through the Earth. If we think of the Earth as a giant magnet whose field lines are outrageous from core to space, we can see how much magnetic flux affects the Earth's atmosphere. So the magnetic flux lines that protrude out from the Earth from the core into space are very important because they help protect the Earth from space debris and also from solar radiation. These fields also help the planet rotate stably around the sun, which is another factor that aids in protection from solar radiation. So our second application, we are looking at the medical field. The working principles of MRI scanners and such machines depend on magnets. The scanner consists of a large magnet that generates a huge magnetic field which passes through the body of the patient. These fields are then collected by a computer which is used to image them and image the body of the patient, in which a physician can analyze them and proceed to make a diagnosis. Another more common example is through microwave ovens. Microwave ovens generate a magnetic field that can oscillate back and forth 4.9 billion times every second. This oscillation causes the molecules to flip and produce friction, which generates heat and is thus used for cooking food. Well, I hope you enjoyed this section of our project, and I hope that you learned something about the daily applications of magnetic flux. Thank you. Alright, we have reached the end of our presentation here today. I thank you so much for watching all the way through to the end, and I hope that you're able to learn something today about magnetic flux and electromagnetic fields. Thank you so much. This has been Cindy Mijaneza and Caitlin DeLong.